Hey everyone, welcome back to Calculus Lesson 4 of Unit 5. In this lesson and the next lesson, we're going to be focusing on the idea of linearization. It's another application of our understanding of calculus, specifically when we're talking about derivatives. The last three lessons, we were focusing on optimization and how calculus can apply to maximizing profits or minimizing costs. Well, here we're going to use this idea called linearization to approximate values that we may not normally be able to determine without the use of a calculator. So some of you might say, well, why can't I just use the calculator to determine these values? And you have a valid point, except for the idea of linearization and the further progression of thought in this mindset in your future calculus classes actually explains how the calculator does calculate these things. So if you've ever wondered, well, how does the calculator know what the sine of 3 is, or the cosine of 78, or whatever it is? Because I can figure out the sine of pi really easily. I can figure out the tangent of pi over 4, the secant of pi over 2. I can figure out all these values pretty easily. But when you get to those values that are in between, it becomes a lot more difficult. And we've been depending on our calculators for so long, but we've never asked the question, why does the calculator produce these answers? How does the calculator think? And this would be the idea of linearization is the introduction to the concepts that the calculator uses in its algorithms to determine those values. So this is a good foundation in understanding why your calculator does what it does and how it works. Okay. So our goal today is to be able to approximate values by looking at tangent lines. Now, the idea, the word linearization, is actually just another word for tangent lines. Now, in the past, I've told you that you do not have to simplify tangent lines. You can leave it in point slope form. You can put it in slope intercept form. It doesn't matter whatever form you want. Anything in calculus, you don't have to simplify unless it specifically says so. So when we're talking about linearization, this is the time when it's specifically telling you to write your tangent line a certain way. And you'll see what that looks like in just a second. But again, linearization, the idea of linearization is just the idea of approximating a curve. So let's say I have a curve, that's my function, and I want to create a tangent line. Well, I find the tangent line maybe at this point here, and I create my tangent line. The tangent line, one idea of a tangent line is it is just a line that is really close to the value of the curve at all the points that are immediately around the point of tangency. Now, obviously, the curve and the tangent line have the same point of tangency, right? They intersect at that one point. And as we move further away from that point of tangency, we can see that the tangent line still holds a pretty accurate value of whatever the curve's value is going to be. But as you get further away, that estimate gets worse and worse and worse. And so to kind of explain what's going on here, let's say I wanted the value of the curve at this point. So I'll call this curve f of x. Okay, this curve is f of x. And the tangent line we're going to refer to as L of x, the linearization. The tangent line is just the linearization. That's all it means. Okay. So f of x is the curve. L of x is the tangent line at that point of tangency. If I were to ask you to find out whatever value this is, so if I wanted you to tell me, let's say this x value is 3, okay, then how would I find that value? Well, that value would be f of 3 if I gave you the function. And you could use the function to evaluate, okay? Not all functions you can evaluate. But let's say I wanted I wanted that value. I can't know that value directly, but what I can know is the value of the tangent line at that point. So we would say that this point is 3 comma f of 3. This point right above it has a value of 3 comma L of 3, right? So these two values are obviously different values. This height is the result when I plug into the tangent line. This value or this height is the result when I plug into the function. But they are really close to each other, especially as we get closer to the point of tangency. So we can conclude this. We can say that f of 3 is approximately L of 3. So if I am not capable of finding f of 3, I can find L of 3 and say I'm pretty close to it. Now again, as you get further and further out, so if I pull this point further out and I want this point here, instead of 3, maybe I want f of 5, finding L of 5 would be an approximation, but it would be an approximation that's a lot further off because we are moving further and further away from the point of tangency. Okay, so that's the idea of linearization. Find the equation of the tangent line, use that equation to approximate the value of the curve at a specific point. Okay, so with that said, uh, again, the tangent line is referred to L of x as in the linearization, okay? And it's used to approximate values of a function. So let's go ahead and take a look at an example of what this looks like. We have, for this example, the function f of x, which is, as soon as it pops up, it's going to tell us that f of x is equal to radical x. And we want to find the linearization at x equals 1. That's our goal. Find the linearization at x equals 1. Well, what does that mean? It just means find the tangent line when x equals 1. Well, we've been doing that all along. First thing we need is we need our point. So we would find the point by plugging in 1 to the original function. So that would be radical 1, which is 1. So our point is 1 comma 1. And we need our slope. Remember, our slope is the derivative. So since f of x is equal to rad x, that implies that f prime of x is equal to 1 over 2 rad x. And remember, if you don't have that memorized, this is x to the 1/2. And then taking the derivative of that would be 1/2 times x to the negative 1/2, which simplifies to this. And then finding the slope, we plug in 1, the x value that we're concerned with, into that equation. And we end up with 1 over 2. So our slope of our tangent line is 1/2. So we would say that the tangent line's equation is going to be y minus 1 equals 1/2 times x minus 1. Now that's fine for a tangent line, and if it just says what is the tangent line, you could leave it like that. But it's specifically telling us to linearize. So we want L of x. We want a function for the tangent line. So in this specific case, we want to isolate y. So we're going to say y equals 1/2 x minus 1/2, distributing 1/2, and then add the 1 there. So we end up with y equals 1/2 x plus 1/2. Or we would conclude that L of x, the linearization, is 1/2 x plus 1/2. And that is our tangent line. But we have a name for it now. It's the linearization. The only difference between linearization and tangent lines is that instead of just leaving it in any form you want, you have to get it so that the y is isolated, and then we call it L of x. Now, the second part of this equation, or the second part of this question says, what is an approximation for the square root of 1.02? So we're trying to figure out what this guy is without the aid of a calculator. Well, if we go back to f of x, we see that f of x is radical x, and we're trying to figure out radical 1.02. So we can figure out radical 1.02 by plugging in 1.02 to my function. You can see that it would be radical 1.02. Now, I don't know that, but what I do know is a tangent line that is really close to the function's value, and I'll show you the graph of this in a second. What I can say, though, is that L of 1.2 is equal to 1/2 times 1.02 plus 1/2. And then I can do this without a calculator. 1/2 of 1.02 is 0.51 plus 1/2 is 0.5. So I end up with 1.01 for L of 1.2. So I found the value of the tangent line, and I will then just extrapolate and say, well, then therefore f of 1.02 is approximately 1.01. Or in other words, the square root of 1.02 is approximately 1.01. So that is my approximation for that value, okay? And we can kind of double check that with our calculator. We can type in the square root of 1.02, and we would end up with an exact value, or a more exact value, I should say, of 1.0995049384. Well, if you go to compare these, you can see that this is actually really, really close to this. We can see that 1.0995, 1.01, this is 0.0005 off. That's really accurate. That is really accurate. Okay. So again, it's an approximation. It's not going to give us the exact value, but it will give us an idea. And so let's go back to the graph of this and understand what we're doing here. So I'm going to go ahead and erase all the work here. And looking at the graph of radical x, here's radical x. And what we did was we found the tangent line when x equals 1, and that point was 1, comma 1. Okay, we found the tangent line of this. That's a little off, but that's okay. Okay, now this is 1. And then, so we have the tangent line. Then we found the value of the tangent line at 1.02 right here, L of 1.02. So we moved over to 1.02. And we said, okay, the value of the tangent line is here. And this graph isn't the greatest. It's hard to see because I got the greatest graph here. Let's say that's radical x. That's a little bit better to look at. So what I found was the value of the tangent line is 1.02. Then I said, well, that's really close to the value of the curve. It is just slightly above it. Okay, that's why we said the L of 1.02 is 1.01. You can see that f of 1.02 is slightly below it, and looking at the original value or the actual value, you can see that it's slightly below it. Again, why would we ever do this if we can just plug it into a calculator? I get it, but this is the way your calculator begins to think. Okay, so with that said, let's go ahead and look at a practice problem for you guys to do and see if you can come up with it here. Let me just double check my work to make sure I'm right. You can ignore the work here. The answer is the same. This work is a little bit wonky. Okay. All right. So for yours, go ahead and pause the video and see if you can answer this question. It says f of x is equal to cosine of x. At x equals pi over 2, we want to find the linearization, and then we want to use that to approximate f of x or cosine of 1.75. So we have f of x equals cosine of x, and we want to find the linearization when x equals pi over 2. So we're going to find our point first. Find the point. So that would be f of pi over 2. So cosine of pi over 2. Well, cosine of pi over 2 is just 1. Cosine of pi over 2 is 1. And then we need to find the slope. The slope is going to be, we got to find f prime of x first. So f prime of x is equal to negative sine of x. And then we have to plug in pi over 2. So we get negative sine of pi over 2. And sine of pi over 2 is, sorry, I got this wrong. Cosine of pi over 2 is 0. Cosine of pi over 2 is 0. Sine of pi over 2 is 1, but we have a negative out front, so that's negative 1. And then our tangent line would then be y minus 0 equals the slope, which is negative 1, times x minus pi over 2. Okay. Now, remember, we want to isolate y and call it L of x because that's minus 0. We can just say L of x equals, I'll go ahead and distribute. We get negative x plus pi over 2. So that is my linearization. That is my equation for my tangent line. Now I want to use that to approximate cosine of 1.75. That's my goal. That's my ultimate goal. Okay. Notice, what am I replacing? I'm replacing from the original function, I'm replacing cosine of x. I'm replacing the x with 1.75. So since I don't know the cosine of 1.75 directly, I can use my tangent line and say, okay, well, what is L of 1.75? That would be negative 1.75 plus pi over 2. And so therefore L of 1.75 is equal to, now this is going to be an approximation because pi is irrational. It's going to go on forever. And this is where I'll probably cheat and use my calculator here to figure out a numeric value for this. But so either way, I'm going to be using a calculator, whether I plug that in or whether I plug that in here. But this is just an example of linearization. So pi over 2 minus 1.75, we end up with negative 0.179. We'll leave it like that. It keeps going, but negative 1.79. Now I could get pretty accurate. I know that pi over 2 is 3.14, 159, let's say 159 over 2. So that would be 1.57 basically 8. Okay, and when I divide that by 2, and then negative 1.75 plus that is going to be the negative 1.79 approximately. Okay, all right. So that's my tangent line's value. So then we can just say that f of 1.75, which is cosine of 1.75, is approximately negative 0.179. Okay, so therefore cosine of 1.75 is approximately negative 1.79. So the question is, how accurate is that? Well, let's go ahead and type into our calculator the cosine of 1.75. So cosine of 1.75 is actually negative 0.178246. Okay, so we're off by about 10 thousandths is what we're off. That's pretty accurate. Now, why was that one off by more than the previous problem? Well, I think it has to do with how far off we were from the point of tangency. What I mean by that is if I look at cosine of x does something like this. And we found the tangent line at pi over 2. We found the tangent line here, okay? We found that tangent line. And pi over 2, like we said before, 3.14 is 1 point, let's see, what did I say? 3.14 is 1.57 divided by 2. So this is at 1.57 approximately. That's the point of tangency. And we were looking for 1.75. So we were actually over here, 1.75. And so we were evaluating this point down here to approximate this point right there, okay, right above it. 1.75 is pretty far from 1.57 comparatively when we were talking about in the previous problem, the square root of 1.02 versus the square root of 1. So it's still pretty accurate, even though we can see there's a little bit of a discrepancy there. Okay, so that is that example. Let me go ahead and double check to make sure I'm right in all of this. Interesting. A little typo there. So negative x plus pi over 2, and then negative 0.18. And this was me in the notes, was actually me not using a calculator because I was just taking the pi over 2 and then just using 3.14 to determine that value. So 1.57 there. So I end up with negative 0.18, which is pretty darn accurate without using a calculator. All right, here's another practice problem for you. It says approximate the value of square root of 120. The square root of 120. Is this an over approximation or an under approximation? We're going to talk more about that later, but let's go ahead and find the approximation of the square root of 120. Now you go, well, you didn't prompt me with anything. You didn't tell me to linearize. You didn't tell me where to find the tangent line. Well, think about it. I don't know the square root of 120, but I do know that the square root of 121 is 11, right? That's one that's really, really close to 120. So if we say this, if f of x is equal to the square root of x, right? And then we find the tangent line when x equals 121, right? So because we can find the square root of 121, we can find the tangent line at x equals 121. And 120 is really close to 121. So let's go ahead and do this. The point is going to be f of 121, which is the square root of 121, which is 11. The slope is going to be, we've got to find f prime. F prime of x is equal to 1 over 2 rad x. And so f prime of 121 is equal to 1 over 2 rad 121, which is 1 over 2 times 11, which is 1 over 22. And then our tangent line is going to be, y minus 11 equals 1 over 22 times x minus 121. So that's my tangent line. Remember, we want to write it as a linearization, so we'd say L of x equals 1 over 22x minus 121 over 22 plus 11. And now I can simplify that further if I need to. This reduces by 11, so I'd end up with 11 over 2 plus 11, so plus 22 over 2. That's L of x, and then that would just be 11 over 2. So we could say that L of x is equal to 1 over 22x plus 11 over 2, plus 11 over 2. So that is my tangent line there. Now I'm going to use that to approximate the value of the square root of 120. So we would say that L of 120 is equal to 1 over 22 times 120 plus 11 over 2. And then we can simplify that a little bit. That would be 60 over 11, let's say, 60 over 11 plus 11 over 22, sorry, 11 over 2. Or we can find a common denominator here. We multiply this by 11, so we'd end up with 120 over 22 plus 121 over 22, which is 241 over 22. That's L of 120. And then as a result, we would say that the square root of 120 is approximately 241 over 22. Okay, so that's going to be 10 point something, 10 point high, essentially. Now we knew that the square root of 120 is a little bit less than 11, but let's go ahead and type it on our calculator just to see how accurate we are. If I said 241 divided by 22, that is approximately 10.9545. Now we can see, I don't know if that's actually an over approximation or an under approximation because I don't know what the actual square root of 120 is. And I don't want to use a calculator to figure it out to compare. That's not the goal. The goal is to be able to use calculus to determine whether this is an over approximation or an under approximation. And so that was the next part of this. It says, is this an over approximation or an under approximation? Well, let me bring this work up here so that I can erase this. So we're going to say, consider the square root of 121 like we did here. We found our derivative. We found our tangent line. So we end up with L of 120 is 1 over 22 times 120 plus 11 over 2, which is 10.955 if I round, okay? So that's fine. Now let's go ahead and look at the function that we're talking about and try and understand what is happening graphically so that we can see what's happening. Let's see here. We got the square root of x, and we found the tangent line at 11. So at 121. We found the tangent line at 121. So it's going to be actually way further out. But we found the tangent line at 121. Oh, it's ugly. Okay. It's a little bit better, not too great. Okay. But then we use the tangent line to approximate when x is 120. So we went back here. Let's say I go way back. Let's say this is 120, way out of scale. But I used the tangent line and I found that value in comparison to that value, okay? Now, what do we notice? We notice that the tangent line is above the curve. So we would say that the approximation is an over approximation. It is above the actual value. Well, what's determining whether it's above or below? Well, let's take a look over here. If I were to look to the right of 121, let's say I wanted to approximate 140. Well, what do we see? We would see that this curve is bending kind of downwards, not downwards, but we have a word for that in calculus. You guys know it, right? But it's not increasing at the same rate as the tangent line is. And so if I'm approximating I'm finding the value of the tangent line, we can see that the tangent line is still above the curve over here. So in this particular case, we see that the tangent line is always above the curve, except the point of tangency. What is causing the tangent line to be above the curve? Okay, so we would again say that this is an over approximation. Why? Because of concavity. We can see that this curve, this function is concave down. This function is concave down because, well, how do I know it's concave down? I know it's concave down because of the second derivative. So let's go ahead and take a look at the second derivative. If f of x is rad x, we would say f prime of x, and I'm going to go to this form, 1 over 2x to the negative 1/2, because I want to get the second derivative. So that would be negative 1/4 x to the negative 3/2. And then if I simplify that, f double prime of x is equal to negative 1 over 4x to the 3/2. Well, looking at concavity here, what do we see? We see that I'm taking the, how do I want to say this? This number on the bottom, no matter what I plug in the bottom, when we're talking about the domain of f of x, remember f of x is equal to rad x. That implies that the domain is all positive numbers, or from 0 to infinity. So I have to plug in positive values of x. If I plug in positive values of x, I get a negative on top always, and a positive on the bottom always. So we can conclude that f double prime of x is always negative. It's always less than 0 no matter what. Therefore, we would say that f of x is concave down. And as a result of that, since it's concave down, we have curvature. It's going downwards. It's concave down. That means the tangent line will always sit on top of it. And since the tangent line sits above it, we would say that the tangent line will always produce an over approximation. Okay, so whether it's over or under is dependent on whether the function is concave up or concave down in the interval that we're talking about here. Okay, so we can see that f double prime of x is always going to be negative there. And I just use an example of 120 in the notes here, but we can see it's negative no matter what based on that domain. Since it's concave down, we would say that it's an over approximation. All right, for this last practice problem here, we're looking to approximate the negative square root of 65. Well, we have to ask ourselves, what value do I know the answer to that's really close to that? And I do know the answer to the square root of 64, or negative square root of 64. That would be negative 8. Because I know that value, I can come to a pretty close approximation by finding the tangent line of the function. So we want to list the function as negative radical x, right? Because the variable that's changing is the thing that's inside here. We're changing the argument 64 to 65. So we're going to call that x. That's the thing that varies. So f of x is equal to negative rad x. So to find the point, we would say f of 64 is equal to negative rad 64, which is equal to negative 8. And then our slope, well, f prime of x is equal to, that got a negative out front there, so it's negative 1 over 2 rad x. And then plugging in 64 to that, we end up with negative 1 over 2 rad 64, which is negative 1 over 2 times 8, which is negative 1/16. Okay? Then our tangent line is going to be y plus 8 equals negative 1/16 times x minus 64. And because I want a linearization, I'm going to isolate y and call it L of x. So that's going to be negative 1/16 x plus 4, and then minus 8. So L of x simplifies to negative 1/16 x minus 4. So that's my linearization. Now I want to use that to approximate f of x when x equals 65. So we would say that L of 65 is equal to negative 1/16 times 65 minus 4. And so this would be negative 65 over 16 minus 4. And I'm trying to avoid using a calculator here. sorry, 65 here. So what I can do is I can separate this to say negative 64 over 16 minus 1 over 16 minus 4. That might work, right? Negative 64 sixteenths minus 1 16th, negative 65 sixteenths. And negative 64 over 16 is negative 4. And that just makes it so I have a mixed fraction. So that's negative 8 and 1/16. So that is L of 65. And as a result of that, we can conclude that the square root of negative 64 is equal to negative 8 and 1/16. Or not equal to, I'm sorry, approximately that. Okay? And that makes sense because, not 64, boy, where am I at here? The negative square root of 65. Well, the square root of 65 has to be a little bit bigger than 8, and we have a negative out front, so it's going to be a little bit further down than negative 8 would be normally. So that is my approximation. Now I want to figure out whether it's an over approximation or an under approximation, and that's based on concavity. So let me rewrite f prime here to be negative 1/2 x to the negative 1/2, and then we'll find our second derivative, f double prime of x. From there, negative 1/2 times negative 1/2 is 1/4 x to the negative 3/2. And then we would end up with 1 over 4 x to the 3/2. And that's f double prime of x. Because the domain restriction of f of x is from 0 to infinity, that means x has to be a positive number, essentially. And if I plug in a positive number here, I will always see that f double prime of x is greater than 0. That's a positive value no matter what, which means f is concave up. F is concave up. And so if you think of a concave up function, I have a concave up function and I have a tangent line on it. Well, that tangent line will always be below the curve if the function is concave up. So since I use the tangent line to approximate the function's value, we can see that it's going to end up being an under approximation. Under approximation. And that's our answer for that. That should actually go right there. Okay. So a lot of little things here, but the bottom line is, guys, it's just a tangent line. Find the tangent line, use the tangent line to determine a value, and then say the curve is about approximately that value. And then we find the concavity to determine whether the tangent line is going to sit above or the tangent line is going to sit below the actual value of the curve or the curve, and then we can say it's over or an under approximation. Let's go ahead and take a look and make sure I'm right before we move on. We have negative 1/16 for our derivative and negative 8 for our point. And so we end up with negative 1/16 x minus 4. And then plugging in 65, we get negative 8.063. And I believe 1 over 16th would be 0.063 or 0.0625, more than likely. So this is a little bit more accurate. It's going to be a over under approximation based on concavity. So we find our second derivative and we determine the signs of our second derivative, which in our case will always be positive, which means the function is concave up, which means we have an under approximation. All right, that wraps up this lesson. Hopefully you have a good understanding of how this all works. If you have any questions, please comment below, and I will talk to you next time.